Section 4.5 has two topics in it. One of them is linear approximations, and the other one is differentials. When you're doing linear approximations, there's a formula in the book that you can memorize and use if you'd like, but it's easier just to think about conceptually what's happening. When you're finding a linear approximation, you're really finding the tangent line to the function at a nearby point where it's easy to evaluate it. You come up with that tangent line, and instead of plugging your x value into the function, which can be difficult, you plug your x value into the tangent line, which is a lot easier to deal with. And here's an example pictorially of what's happening. If I have the function the square root of x, and I would like to put 5 into the square root of x, that's the actual y value here, that would give me the square root of 5. And you can actually use the square root to figure it out, but it's hard to do without the calculator. So what I'd do is I'd pick a point nearby 5 that I can actually take the square root of, and that would be 4. I can find the square root of 4, and that's 2, and so I could come up with a tangent line at x equals 4, which is this red line here. And instead of taking 5 and plugging it into the function square root of x, I can plug 5 into the tangent line instead and come up with an approximation. So here are the steps to finding a linear approximation. First, you want to find a tangent line to the function at a nearby point c, where you can easily evaluate the function. And then substitute the x value you're looking for into the tangent line for x instead of into the original function. And when you solve this for y, you'll approximate your answer. So here's the one we have above here. It's a way to approximate the square root of 5 with a tangent line. That's what the question is. And so what I'd like to do is I'd like to find the equation of the tangent line. Now the function I'm putting the 5 in is the square root of x, because I'm replacing x with 5 there. And I want to find it at x equals 4, because that's a place I can actually evaluate the square root. So to find the tangent line, I need a point on the line. Well, I know x is 4, and when I plug 4 into the function, I get the square root of 4, which is 2. So the y value is 2. But I also need the slope of the tangent line. And to find the slope, I have to find the derivative. Remember, the square root of x is x to the 1/2. So the slope is given by x prime, which is 1/2 x to the negative 1/2. I'm going to rewrite it so it looks nicer. This is 1 over 2 square root of x. I want to find the slope when x is 4, so I plug 4 into my equation for x, and I get 1/4. So the tangent line is y minus 2 equals 1/4 x minus 4. Now there's my tangent line, so I found my linear approximation. And I can write it even nicer by solving for y. Y equals 1/4 x plus 1. 1/4 times negative 4 is negative 1, and I add the 2 over. There's my tangent line. So I'm going to plug 5 in for x into the tangent line, because it's easier to approximate. And I get 1/4 times 5 plus 1, which is 9/4, or 2.25. That's my approximation. Now the actual value for the square root of 5 is 2.24. So my approximation, 2.25, is very, very close. Here's a similar idea, except here they tell you the function to approximate, and they tell you where to approximate it at. So it says find a linear approximation to the sine of x at pi over 4. So I need to find the tangent line. F of x is the sine of x. The x value is pi over 4. To find the y value, I got to put that into the original function, which is the sine of pi over 4. That gives me square root of 2 over 2. So I know a point on the tangent line. It's pi over 4 root 2 over 2. Now I need the slope of the tangent line. To find the slope, I want to find the derivative. The derivative of sine is cosine. And so I take that pi over 4 and I plug it into the derivative to get the slope. And that also gives me root 2 over 2. So the equation of the tangent line is y minus root 2 over 2, because that's the y value, equals the slope, root 2 over 2, times x minus pi over 4. This is the tangent line. You could solve it for y if you wanted to, but there's really no need to. That's the tangent line in what we call point-slope form. So now I'm going to plug in 0.75 into the tangent line instead of into the function. So you'll see me take this tangent line, y minus root 2 over 2 equals root 2 over 2, and instead of x, I'm going to replace that with 0.75. And so I'm going to work out the right-hand side. I get 0.75 minus pi over 4. I'm going to multiply that by the square root of 2 over 2. And so I get y minus root 2 over 2 is negative 0.025. And so I add the square root of 2 over 2 to both sides. And I get 0.682. That's my approximation. If you actually want to find the real value, take 0.75 and plug it into sine, you get 0.6816. So my approximate value is very close to the real value. We can do this one more time to practice. This time they didn't give me the function again, but I can tell that I'm putting stuff in the power of an e. So the function I'm using is e to the x. Now I don't know what e to the 0.06 is, but I know what e to the 0 is. If x is 0, then e to the 0 is 1. So I'm going to find the tangent line at x equals 0 because it's close to 0.6, and I know the y value there. So I know a point on my tangent line is 0, 1. To find the slope, I need the derivative. F prime of x is e to the x. So when I plug 0 into the derivative, I get 1 out for the slope. So the tangent line is y minus 1 equals 1 times x minus 0, or y minus 1 equals x. So my tangent line is x plus 1. So now I want to plug in what I want to use for x. What I wanted to plug in originally was 0.06, and I wanted to plug that into e to the x, but instead I approximated it, and I plugged it into the tangent line instead. So now the equation here becomes y equals 0.06 plus 1, and so I get 1.06. By the way, if you want to find the actual value, e to the 0.06 is 1.0618. So it's really close to the actual value. So all a linear approximation is come up with a tangent line and plug your x into the tangent line. The other topic here is differentials, and differentials is something you also have done before. Differentials relate small changes in the dependent and independent variables, usually x and y. And so here's what differentials are doing. If I want to take the derivative of y, I get y prime. Another way to write that is dy over dx. On the right-hand side, I get 6x when I take the derivative. But dy is really nothing more than the small change in y. And dx is nothing more than a small change in x. So to form the differential, I solve this thing for dy. So I multiply the dx to the other side, and I get dy as 6x dx. This is the differential. And notice, if you tell me what a small change in x is, I'll plug it in for dx, and I'll figure out how much y will change. So the first ones here ask me to find the differentials in the form dy as f prime of x dx. So I'm really going to do the same thing we did before up here. I'm going to take the derivative and multiply the dx over. So 1 over x cubed is x to the negative third. So and I'm going to write this as y equals x to the negative third. Take the derivative, dy over dx is negative 3x to the negative 4, or negative 3 over x to the 4th. So I get dy is negative 3 over x to the 4th times dx. I just multiplied the dx to the other side. That's the differential for the first problem. To do the second one, I'm going to write this as y equals the sine of x squared, because I need the chain rule here. So dy over dx, using the chain rule, is 2 times the sine of x to the first. The derivative of sine of x is cosine of x. So solving this for dy, I get dy is 2 sine x cosine x times dx. And there's my differential. Let's do one more of these differentials here. Here it's 3x cubed minus 4x. I'm going to write it as y equals 3x cubed minus 4x. Now I'm going to take the derivative. Y prime, or dy dx, is 9x squared minus 4. So I solve this thing for dy. I get 9x squared minus 4 times dx, which will give me my differential. You tell me how much x changes, I'll plug it in for dx. I use the start value for x here, and it'll tell me how much y changes. And the real reason we use differentials is so we can solve problems that have to do with changing. You can use differentials to approximate change. In the first example, it tells me the volume of a sphere is 4/3 pi r cubed. And it asks me to approximate the change in the volume when the radius changes. So I need to take the derivative of this with respect to r, because I'll get dv over dr when I take the derivative of volume. V prime is dv over dr. 4/3 pi is a constant. The derivative of r cubed is 3r squared. Notice these 3's will cancel. And so I end up with dv over dr is 4 pi r squared. And dv is 4 pi r squared dr. So the approximate change in volume is dv. My r is the radius that it started at, and the radius it started at was 5 feet. dr is the change in radius, and this radius got bigger by 0.1, so this will be a positive 0.1. And when you work this out, you get 10 pi. Now the units are feet. This is the change in volume, so the volume changes in feet cubed, or cubic feet. So you form the differential, and you plug in for what's changing. Here's another example. The volume of a right circular cylinder is 1/3 pi r squared h. This is tricky because there's r's and h's in here. But if you read the problem, it says approximate the change in volume for a fixed radius. That means that r is a constant. It never changes. It's always fixed. And the height is decreasing. So the things changing here are the volume and the height. So when I take the derivative of volume, I'm going to do it with the height, because those are the things that are changing. The 1/3 pi is a constant, and since r is fixed, r is a constant as well. The derivative of h is just 1. So I multiply the dh over, I get 1/3 pi r squared dh. Now to approximate the change in volume, I can replace my r with what it's always equal to. In this case, it's 20. And I can replace my dh with the change in height. Now the height got smaller. So the height actually changes in a negative way because it's shrinking. And how much did the height get smaller by? It got smaller by 1/10 of a centimeter. So this is going to be a negative 0.1 because it's getting smaller by 1/10. So when I work this out, I get negative 40 pi over 3. It's negative because it's decreasing. I need to put the units on as well. The distance units are centimeters, but since this is a volume, it's centimeters cubed. So differentials are really taking the derivative and multiplying the bottom change over to the other side.